So, hello everyone. Today is our 11th session, and today we will be going more deep into the field effect transistors. So, today is our 11th session. So, we will be going more deep into the field effect transistors. So, in the previous session, we stopped at this problem. Now, let us move towards the another part which is associated with the same problem. This problem was associated with the subthreshold region of the MOSFET, and in the subthreshold region the dependency of the current is exponential. Okay, as you have seen the curve for this ID versus VG, you must have seen this current, it increases exponentially. Okay, then after some time it almost saturates, or it does not change that much. You must have seen this in the lectures. So this is the dependency, this is the simple equation for the current. This, for example, it says that this is the sub-threshold current of the MOSFET, and we had taken this equation and solved it for two current values and obtained the ratio of the subthreshold current in the at two bias points. One was the 0.7 volt and another was the 0.5 volt VGS. So basically, in this problem we are dealing with, as you can see, this will be a long channel device, as this VGS, the operating voltage, the gate operating voltage that we are applying, although the operating voltage is 5 volts, so it means that this material, or this what I can say, this MOSFET is having the long channel, because the sub-threshold region is extended, or you can say this, even for the 0.7 volt, this MOSFET is in sub-threshold region. It means that we will be requiring high amount of bias, that is gate to source bias, in order to move to the saturation region, because the VDD, the supply voltage, which is the VDD, is also high. It is only possible when the device is long channel device. Since we are not dealing with the short channel devices that much in this course, so from this you can just, by looking at the supply voltages, you can say that since this VGS is very less than this supply voltage, operating voltage of VDD, this transistor will be in the triode or the subthreshold region or the linear region. And you have seen this there, that there will be some exponential dependence of the current on the VGS. So now let's move towards the another part of this problem, which says that with reference to the details given in question number 1, we have been told to calculate the total current that must be supplied to the chip at the bias, gate to source bias of 0.7 volts. So it means that there are many transistors on the chip, and the number of transistors that are on the chip are 10 to the power of 6. So we need to bias all these 10 to the power of 6 transistors. Okay, so the gate to source bias, and also they have mentioned for the sake of, what you can say, easiness, so that we can solve the problems easily, they have said that all are biased at same VGS and same VDD, same operating voltage. So we can say that each transistor is given a gate to source voltage of, in this case, in this problem, 0.7 volt, and drain voltage or the operating voltage is simply 5 volts. So if I now find out the current at this 0.7 volt, this ID at 0.7 volts will simply be 10 to the power of minus 5, sorry, minus 15 exponential of 0.7 divided by 2.1 into Vt is 25.9 millivolts. So it's 2.1 into 25.9 into 10 to the power of minus 3. So we had solved for this in the previous case. Sorry, we had directly written it. So let's solve for this. It would simply be 25.9. Let me solve it on my calculator. 2.1 into 25.9 is 554.39. This has to be divided by 1000. It is 0.5439. 0.5439. It's 12.87. So it is exponential of 12.87 into 10 to the power of minus 15. So it is, I would say, it is simply, this value is 10 to the power of minus 15 into 388,481. Okay, this must be in amperes. Yes, it is in amperes approximately. Okay, so now we have to take the number of transistors into account. Number of transistors which are identical. Identical means that all the transistors will be having same threshold voltage. So there will be no shift in the threshold voltage, not even by 0.01 volts for the each transistor. So this is the condition given. So the total current, let me write it down like this. The total current at VGS equal to 0.7 volts would simply be equal to number of transistors, which is 10 to the power of 6 into 10 to the power of minus 15 into, this was 3.88 into 10 to the power of 5. So it would simply be 10 to the power of 11, 10 to the power of minus 3. It will be simply equal to 0.388 into 10 to the power of minus 3 amperes, or 0.388 milliamperes. So option A seems to be the correct option to go with. So this is same problem associated with this question number 1. It says that with reference to this question in 1, we need to find the total power dissipation in the chip at VGS equal to 0.9 volt. So it is simple. We will write down the expression for the ID again. ID is simply 10 to the power of minus 15 exponential of VGS, in this case is 0.9, divided by 2.1 into this thermal voltage 0.0259 or 25.9. So the total current is equal to number of transistors, which is N, into 10 to the power of minus 15. So this value, we need to solve for this. So it is simply 0.9 divided by 2.1 divided by 0.0259, 16.55, which is 1.5, which is 15.36 into 10 to the power of 7, or sorry, since I have written 15, it will be 10 to the power of 6. Okay, so it is simply 15.36 milliamperes. This is the total current at bias of 0.9 volts. Now for the power dissipation is simply the supply voltage or the operating voltage multiplied by the total current. So the power dissipation is simply VDD into I total, which is 5 into, since the supply voltage was 5, yes, the supply voltage was 5 VDD, sorry, it would be 5 into 15.36 milliamperes, so it is milliwatts. So it is simply 15 into 5, it would be 75. Let us multiply this 0.36 as well into 5, it is approximately equal to 76.8 milliwatts. So the option D seems to be the correct option to go with. So we will select this option D over here. Now this problem is related to the gamma factor or the body coefficient that we had seen previously. We had mentioned, we had even derived its units by just saying that it is the multiplication of the two quantities having the unit which was having the root of volt unit, and we required this unit for the gamma. We said that it should also be root of volt in order to have the same dimension across the whole formula. So this gamma is simply given by 2q epsilon s Na by Cox. So this can be simply written to be equal to 2 into 1.6 into 10 to the power of minus 19. Epsilon s is the relative permittivity constant in the silicon. Okay, epsilon s 11.7 into 8.85 into 10 to the power of minus 14, since we are dealing in centimeter units, into 10 to the power of 16. Epsilon ox is simply 3.9 is the relative permittivity constant of the oxide. Okay, into 8.854 into 10 to the power of minus 14 divided by T ox is the thickness. It is 20 nanometers. So it is 20 into 10 to the power of minus 9 meter, or 20 into 10 to the power of minus 7 centimeter. 20 into 10 to the power of minus 7 centimeter. So let's solve for this. 3.9 into 8.854 divided by 2. So it is 1.7 in the denominator, 1.72 into 10 to the power of minus 7. Okay, in the upper we have 2 into 1.6 into 11.7 into 8.854, which is 331.49 into 10 to the power of minus 70. So let me take the square root. So it is equal to 5.756 5.756 into 10 to the power of minus 8 divided by 1.725. 726 into 10 to the power of minus 7. So it's 5.75 divided by 0.726, which is 0.33 root of volt. This is the value of this body coefficient. So the option B seems to be the correct option to go with. Okay, because it is close. It is the 0.33 root of volt. Okay. Now moving towards another problem. It says that this MOS device uh, is which is given in question 4. We have to calculate the change in this threshold voltage when this source to body bias is given. So we have seen this kind of a problem previously. In this problem, it was simply the surface potential term under the square root. We added this source to body bias. It was a simple thing. So this change in threshold voltage was simply delta Vt, and it will be simply this body coefficient considering the surface potential is pinned at 2 phi f minus root of 2 phi. We have to consider this surface potential is pinned at 2 phi f, not at 2 phi f plus something like we used to say previously. It is 2 phi f plus phi naught sort of a thing, but for the purpose of our course we have considered the pinning of the surface potential to occur at 2 phi f. Okay, so this 2 phi f, we need to find this phi f, which is simply we have been given this value, sorry, this Na we have been given except a doping, which is 10 to the power of 16. So this phi f will be Vt, sorry, ln of Na by Ni. Vt is 25.9 into 10 to the power of minus 3, ln of 10 to the power of 16. Ni, I guess, would be 1.5 into 10 to the power of 10. I think they have mentioned it somewhere. Okay, they have not mentioned it. So let's, yes, they have mentioned it to be 1.5 into 10 to the power of 10. 1.5 into 10 to the power of 10 per centimeter cube. So this is the value, this will be the value of phi f. So let's solve for this. So let's solve for this. It is 10 divided by 1.5, sorry, which is 6.66, ln of 6.666 into 10 to the power of 5 into 25.9, which is 0.35. Okay, it comes out to be equal to 0.345, approximately 0.35. Okay, comes out to be equal to 0.34, 0.35. Okay, this is the value of this phi f, 0.347 or approximately 0.34, 0.35 approximately. So now we know this VSB, we know this phi f, we know this gamma, so we can calculate this delta VTH. So this delta VTH, Vt, which will be the change in the threshold voltage, would simply be this gamma factor, which was 0.33 multiplied by 2 phi f. Phi f came out to be 0.35 into 0.35 plus VSB was 1. VSB was 1 minus 2 phi f.
Irusana.
Can you please mute yourself?
Hey, என்னத்த சுத்துனீங்கிற?
Wait a second.
உண்டுனே போ.
Okay, I have muted. So it is simply 0.35 into 2 is 0.7. 0.7 plus 1 is 1.7. So it is 1.7 root of 1.7 minus root of 0.7 into 0.33 delta VT. So let's calculate this thing of 1.7 minus root of 0.7 into 0.33, which is 0.156 something, or approximately 0.16 volt. So let's check the options. Option A is the correct option to go with. So we'll select this option A. Now this is the problem related to the N-channel MOSFET for a long channel, which is approximately equal to 1 micrometer and width equal to 30 micrometer. So the oxide capacitance is given to us, and we have been told to assume that this MOSFET is in non-saturation. As you can see, this VDS is quite less. It is 0.07, okay, and the gate to source bias at that case is 1.5 volts. We have to extract the mobility, so it's kind of a design problem to us. So since VDS is small, MOSFET is in linear region. So the drain current ID will simply be equal to mu NC ox W by L VGS minus VT, which is the threshold voltage, VTH, not the thermal voltage. Let me write it down by the VTH so that we don't get confused, into VDS. Okay, so now for 1.5 volts, the current is 25. ID is 25 microamperes when this VGS is equal to W by L. VGS is equal to 1.5 minus VTH into VDS is, let me write it down by the name of equation 1. For 65 microamperes, the VGS is 2.5 minus VT into VDS. Since we do not know the mobility value, and also we do not know this threshold voltage value, so in order to get rid of this threshold voltage thing, we can simply say that we will subtract the equation first from the equation 2 in order to remove this one unknown. So we will be left with just another unknown, which will be the mobility only. Okay, so we need to subtract equation 1 from 2. So we would simply get this thing to be equal to this 65 minus 25. It would be 65 minus 25 into 10 to the power of minus 6 mu n C ox W by L. This will be 2.5 minus VTH times VDS minus 1.5 plus VTH times VDS. So this thing will plus VTH and minus VTH will cancel out. So we will be left with 2.5 minus 1.5 into VDS. We know this C ox is having the value of 69 nanofarad per centimeter square. So it is equal to 69 into 10 to the power of minus 9. W by L, W is 30 and L is 1. So this is equal to 30 simply into 1 times VDS. VDS is 0.07. 0.07. So from this you can clearly say that this whole thing, let's solve for this, it would be 65 minus 25, which is 40, divided by 69 divided by 30 divided by 0.07. So it is equal to 276.05 approximately. So it is equal to 276.05. This is the value of mu n centimeter square per volt second. So this is the value of the mobility that we obtained. So it is approximately equal to this option C, 276. Okay, this is the value of this mobility that we will be getting. Now let's move towards another problem. Okay, this problem is also, I guess, related to the mobility. It says that we have to consider this n-channel MOSFET with the specifications given uh, in the problem, with W equal to this thing and this capacitance. So this is also the design problem with the same concept that we will be using, that this device is in linear region. Okay, so we will simply use this equation that we used in the previous case, VGS minus VTH, where this is threshold voltage, into VDS. So we will substitute the two values and subtract the two equations corresponding to two gate biases. One would be 2.5 and another would be 1.5. So we will obtain the value of mu n, which is the mobility of the electrons. Okay, so I think we should skip this problem as it is a straightforward one. Now moving towards another problem, which says that which of the following statements are true. So let me ask you people, let me give you I guess couple of minutes so that you can come up with some answer to this. Let it be wrong, so we can discuss upon this problem. So I want you people to answer this question by just giving some logical intuition to every reason or every statement that is present in the problem. Okay, so try to solve this. So can anyone answer this? Let it be wrong.
Answer is 1D, 1, 2, 4.
Okay, can you please give some reasoning? A little bit. I don't need more reasoning.
That means for third option, present trap charges has no effect on CV characteristics of mass system. That means the trapped charge does not affect that voltage and capacitor characteristics of the mass. That is wrong.
Yes,
Remaining statements are correct, I think.
yes, you are absolutely correct. So basically, whenever there is some charge that is present at the interface. For example, it says that in option A, it says that interface states affect the subthreshold swing of a MOSFET due to the presence of additional capacitance. Absolutely. If, for example, we had seen the problem when we had the oxide trap charges, so that oxide trapped charges at the interface, for example, if those charges were positive charges, they helped or they inverted the channel even when the bias was not applied, because the positive bias, that was the positive charges that were present in the oxide, they resulted in the field. As a result of that field, the electrons in the semiconductor near the channel interface were attracted towards the closer to the interface. So the electron buildup was occurring even when there was no bias applied to the this MOS system. So this interface charges and the oxide charges, they largely determine our capacitances, this behavior of the uh, CV characteristics. So the option A is absolutely correct. The option B is also absolutely correct, because because the CV curve, sorry, because the CV curve, because this if I am having, for example, positive charges in the oxide, this will mean that the electron build up in the n kind of a channel. So n kind of a channel, if the substrate is of p type and the channel is of n type, so it means that the electron build up is occurring earlier. So the bias is not even required to build up or to deplete the carriers near the interface. So this would result in the degradation or the decrease of the threshold voltage when the positive charges are present in the P, considering the p-type body. Now if the negative charges are present considering the p-type body, this would repel the electrons. As a result, it will result in the more accumulation near the interface. So more accumulation near the interface would mean that the threshold voltage has now increased, because we will now require more gate to source bias, or gate to body bias rather, I would say. So we will be requiring more gate voltage in order to make the same amount of change, or in order to make the MOSFET move from this accumulation region to the inversion region, because the region is now more accumulated with the holes. So likewise, it means that the CV characteristic, this largely determines is largely determined by the presence of the trap. So it would just these traps will just shift it left or right. So the presence of traps has no effect on the CV, which is wrong. Okay. The charges present at the oxide semiconductor phase has strong effects on the threshold voltage. That is what we were saying, because if the CV curve is shifted, for example, left or right, it would mean that the threshold voltage point is also shifted. Okay, it is as simple as that. So the option D is the correct option to go with. Now, since we were dealing with these long channel devices all throughout this what we can say uh, assignment. Now wait a second. Now we are moving towards this scaling concept, where we try to scale down the, for example, dimensions of the device or the supply voltage of the device. So in this problem we have been told to scale down the some features. So this MOSFET features are scaled down but keeping the voltage scaling as constant. So this means that the supply voltage is not changed, it remains as it was. For example, if the technology was working on 5 volts, now the technology will still be working on the 5 volts, but other parameters like the channel length or the channel width or the rather this channel this gate oxide thickness, etc., they all will change. So in this case, when we are doing this constant voltage scaling, I have a table over here which has been taken from internet source. So if I have to do this constant voltage scaling, I have to scale this channel length by 1 by alpha. So if I am scaling by this alpha, if alpha is scaling factor, if alpha is the scaling factor, so the channel length has to be scaled then by this 1 by alpha. So if for example the channel length was 1 micrometer previously, now this new channel length will be 1 by alpha simply. So it would be divided by this factor. So we will reduce this channel length by this much amount of factor. The substrate doping needs to be increased, okay, considering this constant voltage scaling. Okay, the channel length has been decreased but the substrate doping has to be increased. So similarly it would have impact on the junction depth and depletion layer, and similarly it will be having this effect on the GM, which is the transconductance, which will be same as the current impact. The current would also be impacted by the same factor. The current would increase by the factor of alpha. This would result in the static power dissipation to increase and also as the dynamic power dissipation to increase. So not only we are increasing the current, but we are increasing these power dissipations, the static and dynamic power dissipations, which is highly disadvantageous. Okay, these are the disadvantages because we are having this as, for example, the device is in off state kind of a thing, but still it is dissipating power. For example, previously it was dissipating, let us say, 1 milliwatt. Now it is dissipating alpha milliwatts, where alpha is greater than 1. So it means that we have increased the static power dissipation. So the losses have increased because of this scaling, but the current also has increased by this scaling kind of a thing. The delay has, this gate delay has decreased by this 1 by alpha square, which means that we will be having faster operations. The load capacitance, and keeping this in mind that we had this supply voltage as same, we didn't change this supply voltage. So this gate oxide thickness was also decreased by the 1 by alpha. So these are the things that are associated with the constant voltage scaling. So whenever we are trying to scale the MOSFET features while maintaining the constant voltage scaling rule, we will be doing these kind of a things. So as you can see from this table, the current will be enhanced by the factor of alpha, where this alpha is a scaling factor. So if we are if our scaling factor now is 5, the current will also be scaled or increased by a factor of 5 in the constant voltage scaling kind of a mechanism. Now there is another kind of a mechanism, which is this constant field scaling. Constant field scaling means that V by L, that is the electric field, will remain same. Okay, you can see if we now in this case we decrease the supply voltage by 1 by alpha. Okay, and also we decrease the channel length by 1 by alpha. So E dot dl is the field and V by L will simply be this electric field. Okay, E dot dl was the voltage or the potential drop, I would say. So this E dot dl simply this V has been scaled by 1 by alpha and L has been scaled by 1 by alpha. As a result, E will be same. E will not change. Okay. So now it says that for the NMOS transistor, it means that this the body is of P type and the channel will be N type. As a result of this thing, the channel length is 1 micrometer and the channel width is 10 micrometer. The oxide thickness is 25 nanometer and the substrate doping, which was this p-type doping, is of the order of acceptor doping is of the order of 5 into 10 to the power of 15 centimeter cube. The applied voltage is 3 volt, and if now this voltage is to be scaled using constant field scaling. Okay, constant field scaling means that the electric field has to be remain as it was in the previous case, so it has not to be changed. Okay, with this scaling it has to remain the same uh, through this MOSFET device. So this channel length and the channel, what should be the channel length and the channel width? So the channel length, so this new channel length LCH new will be scaled by this factor, which is this L channel old divided by this factor alpha. Okay, so L channel old was 1 micrometer and the alpha is 1.43. So this would simply be 1 micrometer divided by 1.43. Wait a second. It would simply be 1 divided by 1.43, which is 0.6999 or approximately 0.7 micrometer. So this is the new channel length, which has which would be result, which would be a result of this constant field scaling. Okay, now what would be this new channel width? New channel width will simply be this old channel width divided by this scaling factor. Where is this channel width? Here is the channel width. So the channel width will also be scaled by 1 by alpha. So this is the channel old divided by alpha, which is 10 divided by 1.43 or 7 micrometer. So the option C seems to be the correct option to go with this kind of a constant voltage scaling. Now what should be the oxide thickness of the scale device? So the oxide thickness will also be scaled by this 1 by alpha. So basically all the geometric parameters that are present in this have been scaled by 1 by alpha. This channel length, this width, the depletion layer thickness, this gate oxide thickness, all the junction depth, all are scaled by the 1 by alpha. Okay, so the Tox will also be Tox new will be Tox old divided by alpha. Tox old was, it was, I guess it is 25 nanometer. So it is 25 divided by 1.43 nanometer. So 25 divided by 1.43, it is 17.48 or approximately 17.5 nanometer. 17.5 nanometer. Okay, so this is the value of this scaled oxide thickness in the case of the constant field scale. Now let's move towards another aspect of this, what we can say, mm, another aspect of this MOSFET, which is the uh, circuit analysis of the MOSFET devices. So this problem over here, it it shows that the device, that basically whenever we want to operate this MOSFET, we operate this MOSFET in order to have the mm, uh, what I can say, in order to have this application for the circuits, we operate it in the saturation region. There are specific reasons for that, but rather I would skip those, as the professor must have gone through those reasons, etc. So let's not move towards those things. And let's consider one of the important statement regarding this operation of this MOSFET as a transistor. So this one of the main assumption that, or the main thing that we require, is that the this drain current should be independent of the drain voltage. So it should be it should be independent of the drain to source bias. It should only depend on the gate to source bias. So this is one of the main requirements that we require while operating these devices for the circuit applications. So this is one of the simplest definition, or the simplest thing that we can think of while operating the MOSFET in the saturation region. We require this MOSFET such that this VDS is greater than VGS minus VTH. Okay, so let us draw this, what I can say, this for this these MOSFETs over here. You can clearly see this is the P-type MOSFET, this is the N-type MOSFET, and this is also the N-type MOSFET. So let us draw the small signal equivalents for all these MOSFETs in order to get insights how the MOSFET is solved for this small signal analysis. For the small signal cases, how we can solve this MOSFET, and considering that this drain current has to be independent of the drain bias. It has to be dependent on the gate to source bias only. So let us add some slide. So it would be a bit tricky one. So because this MOSFET, we need to take into account this channel length modulation as well. For all the transistors, it has been told that the channel length modulation is non-zero for all the MOSFETs. So it means that we have to take the output resistance that is associated with the MOSFET, small signal MOSFET equivalent model. So let us draw the small signal MOSFET equivalent model for all these devices. Since we are applying this small signal at this MOSFET M1, this is V in, where we are applying the small signal, and we are taking the output at this at the drain of this M2, or the source of the drain of the M1, or the source of the M2. This is the drain of M1. Okay, drain of M1 or source of M2. So let us draw this small signal equivalents for all three, considering all the DC biases will now be grounded. Okay, in the small signal, all the DC biases are grounded. So let us draw this small signal equivalents. So for this MM1, I will be having Vi applied at the gate. Okay, Vi will be applied at the gate. This is the gate, and the current source Gm, which depends on the gate to source bias, VGS1. This is also grounded. You can say this is also grounded. Okay, this is grounded. Okay, this is grounded. So this is the R naught of 1, which is due to the channel length modulation. So all the transistors will have this resistance associated with them, which will be given by simply this this RD, where this RD is equal to 1 by lambda ID. Okay, so this is the output resistance. Output resistance due to the effect of channel length modulation. So this RD would be present because we have been told to assume that all the transistors are having non-zero channel length modulation. So this is the model, small signal equivalent model for the M1 transistor, and we are taking the output at the drain side. This is gate, this is the source, this is the drain of M1. Let me write it explicitly. Okay, so V0, so this drain of the M1 is connected to the source of the M2. Since this is the P-type MOSFET, it would be source of this P-type MOSFET. This would be the drain of this P-type MOSFET. Okay, so it would mean that the source of the MOSFET in this small signal equivalent case would be grounded. Okay, it would be simply grounded, the source of this P-type MOSFET, because it is connected to the VDD supply, and we are considering the small signal equivalent. It would mean that the gate would also be grounded and the source would also be grounded. So this gate of this MOSFET would also be grounded. So if this is the GM3 VGS3 that is associated with this P-type device, and this is the R0 of this P-type device, this is also grounded because this is the source side of this P-type device. Okay, this was the source side of the P-type device. Yes, this was the source type of the P-type device. It is grounded. Okay, so since this all is connected with this drain, as you can see, this drain of the P is connected to the drain of the M1. Okay, and also the source of the M2. So this is the source of the M2. This is the source of the M2, GM2, VGS2. Okay, this is the source of M2. Okay, the gate of the M2, this is the gate of the M2. Okay, this thing is the gate of the M2. Gate is connected to VDD. This is small signal equivalent, so it means that the gate is grounded. Okay, the gate is grounded. Now the R0 will be the output resistance which is associated with this MOSFET, R0 of 2, and this will be grounded because the drain is connected to the VDD and it is grounded. Okay, in small signal equivalent. So we have this small signal equivalent circuit. As you can see, this VGS3, since this is P-type, it won't be VGS3, it would be VSG3. Okay, it would be VSG3. VSG3 is simply 0. Source is grounded, gate is grounded. So this thing is gone. Okay, now we can simply use the KCL. Okay, let us use the KCL at this node. Okay, it would be simple for us to use the KCL in order to get the insights into this problem. Yeah, so if I consider the current, current is moving from this. Okay, current is moving from this. Okay, current is moving from this, so it will be going into this M1. So if I consider now the KCL, this is the voltage, this voltage is also V0. Okay, since this is V0, this is also V0, this is V0. So if I now consider this point, the current, incoming current from this terminal will be, so let me write it over here, it would be 0 minus V0 divided by R0 of 3 plus, okay, so this could have been done like I would say just by looking into the circuit as well, but since it is our first time, I wanted to do it in an elaborate way so that we get insights how this circuit would behave. So this is the GM2, VGS2. VGS2 is simply, VG is grounded, S2 is this V0 value. Okay, VGS2 is therefore minus V0, V out. Okay, it is minus V out, simply, plus the current which is moving from this, which is 0 minus V out by R0 2. You could have clearly seen that this R0 2, this is parallel to this R0 3. You could have easily seen that as well, considering the uh, cases over here. Rather, I would say this 1 by GM2 should be written. Now this whole thing, sorry, I think I misinterpreted. No, this is okay. So let me write it down. This is the KCL that we are looking. So this current has to be equal to the current moving into this. So this would be GM1 times, this is the GM1 times the VGS1. VGS1 is simply V in minus 0, since S is grounded, so it is V in. Okay, so it is equal to GM1 V in plus this thing is at V out, V out minus 0 divided by R naught of 1. Okay, this is the this is simply equal to the current that is incoming from this node, the currents that are incoming and moving into this this node. Okay, so let me take the V outs on the one side so that we can easily separate them out. It would be minus V out 1 by R naught of 1 plus 1 by R naught of 2 plus 1 by R naught of 3 plus 1 by, not 1 by, it should be GM2. Yes, it is GM2 plus GM2 is equal to GM1 into V in. GM1 into V in. Or simply V out by V in is simply equal to minus GM1 divided by 1 by R naught of 1 plus 1 by R naught of 3 plus 1 by R naught of 2 plus GM2. Okay, so it's simple as that. Clearly 1 by R naught of 1 parallel 1 by R naught of 3 is simply this thing 1 by r naught of 1 plus 1 by r naught of 3. Similarly, 1 by r naught of 2 parallel 1 by gm2 is simply 1 by r naught of 2 plus gm2. So if I substitute this and this in this expression, I would get this V out by V in to be equal to minus gm1 divided by 1 by r naught of 1 parallel 1 by r naught of 3 plus 1 by r naught of 2 parallel 1 by gm2. This itself, this whole thing is simply 1 by r naught of 1 parallel 1 by r naught of 3 parallel r naught of 2 parallel 1 by gm2. So this would simply mean this V out by V in is equal to minus gm1 divided by r naught of 1 r naught of 3, this whole thing parallel to r naught of 2 parallel 1 by gm2, or simply it would mean V out by V in is equal to minus gm1 r naught of 1 parallel r naught of 3 parallel r naught of 2 parallel 1 by gm2. So the options which are matching is option C. Okay, so the option C is matching. So it clearly says that we have been able to obtain the gains in terms of the this channel length modulation uh, uh, encountered resistances. So these R naught 1, R naught 2 and R naught 3 are all due to the output, are all due to the channel length modulation, and this has significant impact on the gain, the small signal gain, voltage gain of the circuit. So you can see this, it depends on the parallel combinations of these R naught values. So now let's move towards another problem which is of similar kind, or rather this is not the circuit problem this time, it is a bit I would say easier than the previous problem. It says that in the circuit which is shown in the figure, both NMOS transistors are identical with threshold voltages being 5 volts. So both the transistors are having the threshold voltage equal to 5 volts. So in this case we have been told to ignore this channel length modulation. So the R naught will not be present in the simulations. And we have been told this, what we have been told clearly for this NMOS, it is gate and drain are connected, so it would mean that the drain to source bias is always greater than VGS minus VTH. So this is in saturation simply. Okay, it is simply in saturation. I think they have given it. Okay, they have not mentioned it. So since they are in series, it would mean that the current through both the MOSFETs has to be equal. Okay, the current has to be equal. So the let us simply say the this saturation current of both the MOSFETs, this NMOS transistors is same. They are in, since they are in series connection. So it would mean this W by L mu N C ox. This is the VGS thing. This is VGS thing for this MOSFET, which would be 30 minus V out. 30 minus V out minus VTH square should be equal to W by L mu N C ox. This MOSFET is having VG equal to 10, source at ground. So it means VGS will simply be equal to 10 minus 5 VGS minus VTH whole square. So this thing W by L, this thing whole thing will go, and sorry, wait a second. Okay, and we will be left with this 25 minus V out whole square is equal to 5 square, or simply 25 minus V out is equal to 5, or V out is equal to 20 volts. So this is the value of the V out. So you can clearly say that this V out is the uh, uh, this is the output voltage value that we have obtained, and both the MOSFETs are in saturation region just by looking into the expressions. Now wait a second. Okay, now moving towards another problem which is associated with the uh, in this time, at this time also, they both the NMOS transistors are the gate and drain are knotted together, so both the transistors will be in saturation. Okay, so since both the transistors will be in saturation, okay, so it means that we need to find out the saturation current for the MOSFETs in order to find the ratio of the W1 and W2. So let us say that since the both MOSFETs are in saturation, wait a second to check this thing. Okay, I guess it is recording. Yes, wait a second. Okay, display capture is on, but why isn't it showing like this? Okay, it's fine. So both the MOSFETs are in saturation. As you can see, the drain and the gate is knotted together for both the MOSFETs. So the saturation current will simply be 1 by 2. Okay, I forgot 1 by 2 over. It shouldn't have mattered because this would have got cancelled. So, but it should be written. So it is 1 by 2 mu n C ox W1 by L1 VGS. Okay, for this MOSFET VGS is simply 1.5 volts and VTH is 1.2, so it would simply be 1.5 minus 1.2 whole squared equal to 1 by 2 mu n C ox W2 by L2. and for this MOSFET VGS is 3.5 minus 1.5, which is simply equal to 2. Okay, so it is 2. This is equal to, sorry, this I should write it over here. VGS 2 is equal to this thing. Okay, so this is 2 minus 1.2 whole square. So all these terms will go, since L2 is equal to L1, it has been given to us. So we will be left with W1 times 0.3 whole square is equal to W2 times 0.8 whole square. So it is equal to simply 64 by 9 W1 by W2. So let us divide this number. 64 divided by 9 is simply 7.11. It is 7.11. This is a W1 by W2. So the option A seems to be the correct option to go with. Okay, let's move towards another problem. So this problem is associated with this a circuit which says that in the circuit which is shown in the figure, the threshold voltage of the MOSFET M is 0.5 volts and Vin is 1 volt. Okay, this is equal to 1 volt. Okay, the DC output voltage is equal to 1.5 volts. Okay, the channel length parameter is also given to us. Okay, lambda is given to us. Lambda is equal to 0.09 volt inverse. Okay, it's fine. So what we are required to find, we are required to find the current in this device. This current we require. So we can simply say using KCL at this point. Okay, we can say the current incoming from this is simply 3 minus V out divided by 10K is equal to ID plus the current V out minus V in divided by 10K. Okay, or simply ID will be equal to 3 minus V out is 1.5 divided by 10K minus V out is 1.5, V in is 0.1, 1, it means that 1.5 minus 1 is 0.5 divided by 10K. So it would mean simply it is 1 divided by 10, it is 1 divided by 10K, or it is 0.1 milliampere. This is the value of the current. Okay, that we will be having in the flowing through this MOSFET device. Okay, so now we have been able to find the current, which is 0.1. So we will select this option B. There is another problem associated with it, which says that with respect to the details which are given in question 6, we are required to find the aspect ratio of the device. So we need to find the W by L of the device. So let's move towards this problem again. We have found out ID. This VDS is equal to 1.5. VGS minus VTH is simply equal to 0.5. VDS is greater than VGS minus VTH. So the device is in saturation. Okay, that is the first thing. So since the device is in saturation, we can simply write down the solution for this. by finding the current 1 by 2 mu n C aux W by L VGS minus VTH whole square. But there's one trick over here. We will be having this channel length modulation as well. So the lambda has to be taken into account, and as a result of this thing, there will be drain to source bias dependency of this drain current. So this drain current is dependent on the VDS in this case. Now let's take the values for these things. So it is simply equal to 0.1 milliampere is equal to 1 by 2 into 0.1 into 10 to the power of minus 3 W by L. We require VGS minus VTH. VGS minus VTH is 0.5. It is 0.5 whole squared. 1 plus lambda is 0.09. VDS is 1.5. VDS is 1.5. Okay. So let's solve for this. This thing and this thing would go, this thing and this thing would go. So we will be left with 0.09 into 1.5 plus 1, 1.135 into 0.5 into 0.5 divided by 2. It is okay. It is coming out to be equal to 1 divided by 0.14. So it comes out to be equal to 7 approximately. So we will select the option D because none of our option is matching, because it is coming out to be approximately equal to 7. So I guess it okay. Let me stop here for today. So if we are having some questions, we can answer them. Otherwise, we will start the circuits again in the next session, and hopefully that will be most probably our last session. So if we are having some questions, please feel free to unmute yourself and answer and ask the questions.
Yeah, I have one question, sir.
Yes.
Yeah, regarding one problem, if the R naught is very less,
Yes.
if R naught is very less, I can consider that R naught into the calculation, or I can neglect that.
It depends. If it has been told by the professor in any problem that you have to take the channel length modulation, then please take the channel length modulation. But if it's mentioned, if it has been mentioned that you can neglect the R naught, then it is better to neglect it. If you want to take it only when the professor is mentioned.
Okay. And regarding assignment, I want to some answer, sir. That
Okay.
means 10th question marks are not updated yet.
Okay.
And in week 8 or 9, I think that one question I raised the query, but I didn't get any response.
Can you please email that question to me, because I do not look into that thing, that chat thing. So if you can email me that problem, I can I,
Okay.
I can try to solve it, and I will send you the solution by email. And if everyone is interested in that problem, and if I feel that problem is for everyone, I will just discuss that problem in next session as well. But I will send you the solution right away. The moment you
Okay.
send me the problem, I will get some time in the evening. I will solve that problem for you, and I will respond to your email by that time. So
Okay. Okay. Thank you.
you can email me. Let me write down my email over here. It is a sorry. Let me write it down. It is ATEEB 20 at iitk.ac.in. Okay.
Oh, okay, sir.
Okay.
Okay.
You
Thank
can.
you, sir.
Okay. Mr. Vinod. So if there is no question from any one of us, I request you people to please leave the session. So, but if you have question, you are again welcome to ask. So, if there is no question, we can end the session. So, thank you for joining the session. Let me stop the recording.